Hello, this is Mr. Sorrentino again, and this is another video for Math 31. We're now moving into Chapter 5, and the reason why we're going to focus some attention on inverse functions in 5.1 is because that the rest of this particular chapter focuses on the relationship between a set of inverse functions, one being an exponential function, the other one being a logarithmic function. And since they are inverses of each other, and some of the characteristics we're going to note are because they are inverses, it becomes a good thing to focus our attention on knowing what inverse functions are and how they relate to one another based on them being inverses of each other. So we start with talking about an inverse relation first. Now, when I mentioned something about an inverse relation, it holds true for an inverse function too. But the inverse of a relation occurs when the domain and range are switched. That's basically all it is. So if I'm given like ordered pairs or a table of values like in example 1, all I have to do is reverse the coordinates. If I'm given a formula, I interchange the variables in the two-variable equation, and then I typically solve for the new y variable. So for instance, this relation here. Now this is a function. You notice that all the x values are only mentioned once. So I mean every x is paired with exactly one y. But if I want to say what the inverse is, my x's and y's interchange. So the x coordinates would be the 7, the 6, the 5, the 6, the 7. And the y's would be the -4, -2, 0, 2, and 4. Now, as you can see here, the inverse is not a function here. Because if you look at like an instance of the 7s as well as the 6s for the x's, a 7 produces a -4 and also a 4. The input or x value is 6 produces a y value of -2 and 2. So for those reasons, this is not a function. And you can also see that graphically. I also provide this on your notes. You know, this is what the original one looked like. So the original one is a function, but the new one isn't, because in two places, namely here and here, it fails the vertical line test. So when you have ordered pairs in some way, either in table form or if they were listed as points, all you do is reverse the x's and y's and you would have the inverse of that. I want to find the inverse of the following functions. Now these are functions. This is a linear function. This is a quadratic function. They're functions. There's a note down here. Even if a relation is a function, its inverse is not necessarily going to be one. And we want to be able to keep that in mind because we're going to look for ways of determining how do we know if it is or is not the case. Well, the first thing I do, if it's written in function format, I'm going to replace f of x with y. And now I'm going to do the inverse. I usually indicate that I've done an inverse by putting a little I there with a circle. I mean, this is just my notation for it. Because the reason why I want to note that is because if I put x in the place of y and vice versa, I'm changing what the x and the y are standing for. See, in this instance here, y was a function of x. Once I do the inverse at this point, y is no longer the function of x. Y is going to be the inverse of f of x. Now we have a notation for that if it ends up being a function. I have to see though if it's going to be a function. And the way I need to do that now is at this point, I now need to solve for the new y. So I want to get this y now by itself. I'm going to add 5 to both sides. Now I'm going to divide both sides by 2. So here y is going to equal, I could keep it as x plus 5 over 2 if I wanted to. I could also just distribute that and say that's 1/2 x plus 5/2. I could also write the 5/2 as 2.5. It doesn't matter. Well, this is in slope-intercept form. It's a line. And unless it's a vertical line, which this isn't, this is obviously slanted, it's going to be a function. So I can now say at this point that, replace the y, I could say that the inverse of x, the inverse of f of x is 1/2 x plus 5/2. This is a function notation, okay? Which indicates that, that the inverse of this function is also a function. When I look at b, on the other hand, again, I'm going to let y equal f of x at first, and then I'm going to apply an inverse. So now I'm going to have x where y was and y where x was. Again, so a couple of notes. I'm not going to keep making these notes all the time. Here, y was equal to f of x. That was the assumption. That's why I was replaced one with the other. Here, however, y again is the inverse of f of x. Now, I don't know yet if it's a function or not, so I'm not going to start saying that y equals f negative 1 of x. If I could show that it's a function, okay, I'm done. I could then use the function notation. So I'm going to start solving this new equation for y. So I'm going to add 16 to both sides. And then I would need to square root both sides, but as usual, when I put a square root into a problem where it previously did not exist, that plus or minus symbol has to come with it. So I would end up with y equals plus or minus the square root of x plus 16. This is not a function. And therefore, I would not be able to write it in a notation like I had down here. This is not a function. The only way I'd be able to write this as a function, and I'll talk very, very briefly about this towards the end of this lesson, is if I restrict the range of this inverse, which means I should also restrict the domain of the original. And we'll get more into how those two things relate to each other. So, this is the best I could do for stating what the inverse would be. However, that's not a function, and that's not a function because we talked about it before, because this thing shows up. That gives me several instances, like for instance, if x were to equal 0, that would produce a y value of 4 as well as a y value of negative 4. Producing two y values from a single x value is a sign that you do not have a function. So, and again, you're showing some graphs of the situations to verify this. So in A, here's the original function, here's the inverse. Well, they're both lines. They both pass a vertical line test. They're both functions. Whereas here, if I have this parabola and I plotted these various points, these would be points on the parabola. If I would reverse, their coordinates and rewrite them this way, obviously this fails the vertical line test, horribly. So, there's not any x value except for negative 16 that only produces one y value. So it's not a function. So now let's talk about a few things that helps us figure out if a function would be an inverse function or not. A horizontal line test. It's very similar to the vertical line test. A vertical line test will help us determine if a relation's a function. The horizontal line test will allow us to determine whether or not the inverse of a relation is a function. So if I have a situation where I pass a horizontal line through the graph of a relation and that horizontal line passes through more than once, then I know for sure the inverse will not be a function. Now that could be instances where the original relation is not a function either, or it could be an instance where the original relation is a function, but the inverse is not going to be. Another term you're going to start seeing is that is the term of being one-to-one functions. A function is one-to-one if and only if its inverse is also a function. That means that if you have a relation it has to be first be a function. So it has to be a one-to-one, let me emphasize it, a one-to-one function. You cannot have a one-to-one function if it's not first a function. So another term that you're going to see, let me scooch this down a little bit, some properties of these one-to-one functions. And we're going to show how to use these various things. So if A doesn't equal B, then f of A doesn't equal f of B. So basically, different x values should always produce different y values. So I shouldn't see any repeating y values either. Terminology, as I've shown before, f of -1 of x is how we would indicate it's the inverse of f of x. So same thing, if I had the inverse of g of x, I'd say g -1 of x. I'm not raising this to the -1 power. This -1 doesn't mean I'm taking the function and raising it to the -1 power, or I'm putting it in the denominator. So if I say, oh, here's f of x equaling x plus 2, f -1 of x is not me doing 1 over x plus 2. When I'm using it with function notation, this is not the case. This means that f -1 means inverse. It doesn't mean reciprocal, okay? So keep that in mind. If it's a one-to-one function, the domain of f of x is the range of the inverse, and the range of f of x is the domain of the inverse. That's how we can sometimes more easily find domains and ranges when we have functions that are inverses, because at the point that I'm saying, well, I know what the domain is, I don't know what the range is. Well, if I find the inverse of that function and it still is a function, then I know that the domain of that new function will be the range of one that I had done with the inverse of. And this is the last test we use for this. If I have two functions, and if I do a composition of those two functions in any order, and that comes out just to be x, then that shows me that those two are inverses of each other. So we're going to make use of these various properties to answer various questions for the remaining examples. So let's have a look at them. So for example 3, you're given some functions. You're given both the formula and you're given a graph, and you're asked to determine if the following functions are one-to-one. So these are all functions. You're going to notice with each one of these graphs, each one of these graphs they do pass the vertical line test. We want to be able to show graphically and algebraically that they are also one-to-one. So basically what we have to do is find a way of determining if the inverse is also a function. So one way of doing that, if I have the graph, f of x equaling x squared minus 6x plus 8, it fails the horizontal line test. So I can say, from graphically, it's not one-to-one. As far as algebraically goes, I kind of outlined that before. How would I show algebraically that it's not one-to-one? Well, what I would do is rewrite it with y equals x squared minus 6x plus 8, and then I would find the inverse, which means the x and the y get changed around, so every x becomes a y, every y becomes an x. Now, here's the first instance. I'm trying to solve this for y. I want to get y equals something with an x in it. I mean, I would say f of x, but I don't know if it's a function yet. But I want to get y written as some expression of x. That means I don't want to have multiple y's in here. So I have to try to figure out ways of taking this equation here. Now, I don't have it set equal to 0. So I kind of lose my ability to use the quadratic formula. And I kind of lose my ability to use factoring, because those only work when I have it set equal to 0. So for me to do this, the only way for me to possibly solve this and get y equals something in terms of x, I have to use completing the square. So what I'm going to do is I'm going to say, okay, I'm going to subtract the 8 from both sides, and I want to complete the square. And we've talked about this method before. I'm going to take half of this middle term. I'm going to square it, which makes the left-hand side a perfect square trinomial. I've added 9 to the left-hand side, though, which means I have to also add 9 to the right. I had to account for that. And so the y squared minus 6y plus 9 could be rewritten as y minus 3 squared is going to equal x plus 1. So now I only have one term that has a y in it. Everything else doesn't. I could use basic equation solving at this point to solve this. So scooching this down a little bit, I could square root both sides, and here's where I lose. Here's where it becomes evident that this is not going to be a function. When I take the square root of both sides, I'm treating y as the variable, so the non-variable side is the x plus 1. So when I square root that side, I have plus or minus the square root of x plus 1. And then when I add 3, I get y equals 3 plus or minus the square root of x plus 1. Because of that plus or minus symbol right here, there are values of x, say 0, where I could get more than one y value. Because if x is 0, y is going to be either equal to 3 plus the square root of 1, which would be 4, or y is going to equal 3 minus the square root of 1, which is 2. 0 as an x value producing two y values means that this inverse I came up with is not a function. So, and that leads me to go back up to the same conclusion I made before. This is not one-to-one. Getting to the next one, f of x equals the square root of x minus 1. As you can see, it's a function. It also passes the horizontal line test. No matter which horizontal line I draw through, it's only touching the graph once. So this passes the horizontal line test. And therefore I could say this is one-to-one. How am I going to show this algebraically? Well, again, I'm going to replace f of x with y. Often with these functions, I should still be noting of the fact that, we don't have to get into this much detail with this. This is more so things you might have to do when you get to pre-calculus and such. Keep in mind that the domain has to be going from 1 to infinity. And we are talking about the positive square root. So my y value has to go from 0 to infinity. When I do the inverse of this, so applying the inverse, switch my y's with my x's, so this becomes an x, this becomes a y. I have my inverse. Now I want to solve for y, so I would square both sides. Squaring gets rid of square roots. And then I would add 1 to both sides. I'm just going to move the y to the other side, so I'm going to have y equals x squared plus 1. Nowhere in the process of doing this did I have to put a plus or minus symbol in. I got rid of a square root. I didn't bring one in. So, this is a function. Now, technically, from the other properties, this function would have to have a domain from 0 to infinity. Where you say, well, wait, it's a quadratic. It doesn't have it isn't going to have a domain restriction. Well, the other reason why this has a domain restriction technically is because the range of the original function was restricted, and the range of the original function is the domain of this one. And if I choose values of x that are 0 or more only, well, then my range would be values of 1 or more, which would be the original domain. I can see that no matter what horizontal line I put through this, it passes the horizontal line test. Gets a little bit iffy here because of the fact, but you have to remember, this is probably your horizontal asymptote. And as you can see, I know the horizontal asymptote for this based on what we've talked about before. Same degree on top and bottom, it's y equals 1. And this is happening when y equals 1, this line right here. So it's avoiding it like an asymptote, which means it's getting infinitely close, but graphically, it is 1-to-1. It is a 1-to-1 function. The domain is everything but 3. And as we just discussed, the range, based on the graph I see, and me knowing about the horizontal asymptote, it's anything but 1. We're keeping this idea in the back of our mind. As I said, you don't necessarily have to do this. So if I wanted to find the inverse of this function algebraically and see if it was a function, I would set first y equals x minus 2 over x minus 3. I'm going to do my inverse, where I can now say that I have x equaling y minus 2 over y minus 3. Now again, my goal is to get y as some expression of x, which means I want y alone on one side, and on the other stuff I want to have x's, constants, and that's it. I don't want any y's on the right hand side. So I'm going to have to do some manipulation with this in order to get this solved for y and only y. So what I'm going to do with this is I'm going to pretend as though that this is like x over 1, and I'm going to cross multiply. So I'm going to have x times y minus 3 equaling y minus 2, or make sure that's in parentheses. I want to get y alone on one side of this equation, but I had to make sure I got the one y out of the denominator. I'm going to distribute this xy minus 3x equals y minus 2. In order for me to start working towards getting y alone, I'm going to get everything that has a y on one side of the equation and anything that doesn't have a y on the other. With that in mind, I'm going to subtract y from both sides, and I'm going to add 3x to both sides. So what happens here is, well, the y and minus y on this side cancel, the 3x and minus 3x on this side cancel. So I'm left on the left-hand side with x, y, minus y equals 3x minus 2. So all my y's are on one side of the equation. I can't combine these together because an xy term and a y term are not the same. I had to figure out a way, though, to get this down to having just a single y being mentioned. Well, both terms do have a y in it. This is like saying x times y, this first one. This one's like saying 1 times y. So I can look at this as being y times, factoring it out, x minus 1. And then when I divide both sides by x minus 1, that's the function I would get. It is a function because nowhere in the midst of me solving this did I have to use that plus or minus symbol. Every x value will produce exactly one y value. So I could then rewrite this now as an f negative 1 of x equaling 3x minus 2 over x minus 1. This one has a domain of everything but 1. which you can see up here was the original range, or the original, yeah, the original range. We brought that up. And therefore, and because of the test, we know it has a horizontal asymptote at y equals 3. The graph in its entirety, avoid that y equals 3. I'd see that the range goes from negative infinity to 3, and then from 3 to infinity, so everything but 3 as well. Rational functions, if tend to have a lot more cases where it's 1-to-1. Well, graphically, I mean, it's a function we talked about before, and it does pass the vertical line test. It does not pass the horizontal line test. So I can say it's not 1-to-1. It's not 1-to-1. I can see that it's failing the horizontal line test badly, which means if I do its inverse, it's going to tend to look more along the lines of this, and it's going to fail the vertical line test at that point. How am I going to show this algebraically? Again, I'm going to let y equals the absolute value of x plus 5. So x is going to be the absolute value of y plus 5. I want to solve this for y. It's not very difficult to solve. I mean, I want to get that plus 5 away from the y, so a subtraction of 5 is going to happen sooner or later. But I can't move that 5 until the grouping symbol absolute values is gone. The only way to get rid of an absolute value is to, and now here's where we get into, possibly for extraneous solutions and things like that. We don't know what x is. X could be positive, x could be negative. We're going to assume it's positive. So we work under, anytime we work under an assumption, we get a possibility for extraneous solutions. I'm going to treat x as if it were positive, and I'm going to say, well, I know that y plus 5 then would equal either plus or minus x. I would usually say x or negative x, but same thing. This plus or minus right here automatically already tells me it's not going to be a function. So if I finish this off, I have that it's negative 5 plus or minus x. That is enough to indicate that it is not a function, because that plus or minus symbol means that values of x are going to produce more than one value of y. So I can say here this is not a function, which comes back up to here telling me it's not 1-to-1, because I just did the inverse and it's shown that the inverse is not a function. Now these are both rational functions, okay? I could talk about the domain and range first without actually going into the process of saying, are these in fact inverses? I want to verify that, but just to kind of move into the discussion we're going to have briefly in example 5, I want to look at domain and range of these two functions. Well, the domain for this one is pretty easy. It's all values of x except -1, because -1 would create a 0 in the denominator, and that means it won't exist at that point. I know this thing has a horizontal asymptote at y equals 0, because I have degree 0 up here, degree 1 down here. The highest power of x on top is smaller than the higher power of x on the bottom, which means we have a horizontal asymptote at y equals 0. Now, just because it has a horizontal asymptote there doesn't mean that the graph can't pass through it. If it passes through that asymptote, it's not a range restriction, but I have to say, okay, well, is it possible for 3 over x plus 1 to equal 0? From a logic standpoint, if I take 3 and divide it by a number, I'm never going to get 0. I cannot divide a number by anything and end up with 0. It's impossible. I could get really close. I could get it to be really small, but it's not going to actually equal 0. I could also sit there and think of more of like cross multiplication. Well, if I assume this is allowed to happen, then if I cross multiply, I would be able to get 3 equals 0 times x plus 1, which means 3 would equal 0. Well, this is false. Now, with this information all together, I could say that the range is anything but 0. So that works just fine. This other function, let's talk about the domain. Well, the only issue I'm going to have with the domain, for this one, is if x equals 0. So x should not be 0. Based on the same rules that we talked about, prior, this has a degree of 1, highest power of x. This has a degree of 1. Therefore, this should have a horizontal asymptote at y equals, it's a ratio of the leading coefficients. There's a negative 1 in front of that one, so it's negative 1 on top. There's a 1 in front of this one, 1 on the bottom. So negative 1 is a horizontal asymptote. Doesn't mean it's a domain restriction. So the thing I have to ask myself is, well, can 3 minus x over x equal negative 1? Well, let's find out. Assuming that it works, I cross multiply, I would get 3 minus x equaling negative x. I would then add 0 to both. I would try to get x on one side by adding x to both sides, and that would give me that 3 equals 0 again, which again is false. So I know that 3 minus x over x cannot equal that negative 1, which means that I can now state that the range for this, at least I've established so far that the domain of the domain of f of x is the range of f negative 1 of x, and that the range of f of x is the domain of f negative 1 of x. Having the domains and ranges like this does not make them inverses. That alone. That's what I had to determine. So one way that I've kind of already shown enough of, but I'm just going to mention it, is if I start with f of x and go through the process of letting f of x be y, do the inverse by switching x's and y's, and then solving, do I end up with this? If it happens, then that's a good enough way of showing it. So another method is to use that test that we talked about, and I'm going to rewrite it down here. I'm going to run this test, and if this works, I have to show both of them. If I do this, and one of them doesn't come up to be x, then I know they're not inverses. So I can actually do this to show that things are not inverses as well. It's actually more streamlined, because as soon as I do the first one, if I do the composition and find out I don't get x as a result, then I know they're not inverses. I don't have to test the other way around. To show that they are inverses, though, I do have to show both of these. And that's because there are some functions, we're not going to study any of them in this course, but there are some functions, because remember, composition is not commutative. I can compose them in one way and get x, but I can compose them in the other way and get something else. That would mean they're not inverses. Let's see what happens when I do f negative 1 of x, which of course would be interpreted as this. Now, I have x in the parentheses, so I know I'm looking to get an expression, which means that the only thing I can really do, working my way from the innermost parentheses out, is I'm going to put the formula in here for f negative 1 of x, which means I'm going to go to the function f of x and replace every x with a 3 minus x over x in its place. I had to simplify this. I mean, if for no other reason, that I don't really like having fractions with fractions in them. So if I can get rid of the fraction bar in the denominator, that would certainly be helpful. So I'm going to multiply the entire bottom by x, because that will get rid of the fraction in the denominator. But again, I can't do anything to the top that on the bottom that I can't do on the top, because if I do that, I'm changing the value of it. So I'm going to multiply this by x over x, which means I'm multiplying this by 1. On top, I get 3x. On the bottom, I'm going to have to distribute that x. 3 minus x over x is just going to be 3 minus x. Positive 1 times x is going to be plus x. So I have 3 minus x plus x on the bottom. The minus x and plus x cancel. And that equals x. So far, I got that established. Now if I do f negative 1 of f of x, that's the same thing as f negative 1 of f of x. Working my way from the innermost parenthesis out, and again recognize I'm going to get an expression. I'm going to replace what's inside here with 3 over x plus 1, because that's what f of x is. Which means I'm going to go to the function f negative 1 and replace every x with 3 over x plus 1. So I'm going to have 3 minus 3 over x plus 1 all over 3 over x plus 1. So now I have both the numerator and the denominator having fractions in them. However, if I multiply the top and bottom by x plus 1 over x plus 1 here, that's going to cause some cancellations to occur to allow me to simplify this. So I'm going to have 3 times the quantity x plus 1 minus 3 over 3, which gives me 3x plus 3 minus 3 over 3. These, of course, become nothing. I end up with 3x over 3, which is just equal to x. So I've proven that if I compose them in either direction, I get x, which allows me to conclude they are inverses. And so it stands to reason why we had some of the results we had above, where the domain of one was the range of the other and vice versa. Example 5 it's listed as optional, and the reason why it's listed as optional in previous versions of this course, if I started doing this flipped classroom model, I would usually only get into it if there was enough time in class. But I do want to talk about it only because of the fact that I think it makes some things about going into pre-calculus and calculus a little easier. And that's why I'm looking at these two domains from example 3. These were the ones that weren't one-to-one functions. And so when I look at these original functions and the original graphs, the original domain of this function was any real number, because I can put any real number into a quadratic function and get a number. The original range went from, well, this one had a vertex, and we can see where that vertex was on the graph. Looks like the vertex was at 3, negative 1. And so we had that graph originally. Here's 3, negative 1, and the graph did something like this. The vertex was at 3, negative 1. The range was therefore negative 1 to infinity, because the lowest point was negative 1. And when we did the inverse of this, going back to the inverse, we came up with this. From our previous work, was y equals 3 plus or minus the square root of x plus 1. I wouldn't have an issue if the inverse was 3 plus the square root of x plus 1, or 3 minus the square root of x plus 1. If it was one of these but not one of these or the other but not both, it would be 1 to 1. So for me to restrict the domain of the original function f of x in order for me to make this 1 to 1, I don't want this to be negative infinity to infinity. I want this to produce only a specific range in the new function, which means that since I have two values for y here, my options are just to pick one. Now, I could pick either of them. I'm just going to pick this one. If I have y equaling 3 plus the square root of x plus 1, and I want to know stuff about this range, this goes back to some of our graph transformation things. We have a parent function of y equals the square root of x. This indicates, and y equals the square root of x, we know starts at 0, 0. It's the lowest point. Then it has 1, 1, 2, 4, or 4, 2, 9, 3, so forth and so on. So we know that this has a range from 0 to infinity. But if I put the plus 1 inside the absolute value mark, it's going to cause me to shift left 1. That's not going to change my range. The 3 on the outside, though, is going to cause my range to go up by 3. So this, I expect to have a range going from 3 to infinity. In a very similar fashion, by the way, I would expect this one to have a range going from negative infinity up to as far as 3. Well, these would be one of your best options to restrict your domain. If I said here the range instead is now 3 to infinity, that means that I'm saying that only this part is what I'm considering part of the graph. The other part I'm more or less ignoring. And therefore it would be 1 to 1, because at that point, if I'm only looking at that half of the graph, it would pass the horizontal line test. So that's how you can determine a good way of restricting the domain. I could have also used this one and just dealt with the left side of the graph. Well, getting to this one here, the original domain, well, I could put any number in to an absolute value function. Of course, the original range, since I'm taking the absolute value of something, I expect it to be 0 or more. And I can see this on the graph. Going back to what we had for the graph, and I'm just making a quick sketch of this. Here's at negative 5. The graph did something along the lines of this. When I looked at my inverse, I either had y equals negative 5 plus x, or y equals negative 5 minus x. Those are what I resulted in. These, if I find out like what these ranges would have, and remember on the inverse, this x here is the range of the original function. So I know on the inverse, the domain are x values that are 0 or more. So if I'm adding a number that's 0 or more to negative 5, that means that negative 5 is going to be the smallest of those numbers. So the range is going to go from -5 and just keep getting bigger from there. If I have it the other way around, and I'm subtracting a number that's 0 or more, the -5 is going to be the biggest number I have. Just going to get smaller from there. One of these two would be the best way to restrict the domain. I'm just going to choose this one here and say, okay, well, the restricted domain to make this 1-to-1 would be -5 to infinity. Because again, what I would be considering at that point is just this portion of the graph. The other portion I'd be ignoring, and if that's all the graph I'm considering, that is passing the horizontal line test. Section 5.2, exponential functions and their graphs. An exponential function, I mean, powers are involved, but notice the main difference is that, we were used to situations, with polynomials, we had x raised to the n power, and we had maybe multiple terms of that. Notice now that we now have the number as the base and the x as the exponent. That's what makes them exponential. We're always going to assume that a is greater than 0, because if we have a base that's negative, that creates a different situation altogether. If I have a negative base, then raising it to an even number power, even integer power, would make it positive. An odd power would make it negative. There are some powers that wouldn't work at all, like fractional powers. So we would run into some issues with continuity and things of that nature. So we don't really consider those. What's important about that is if I have an exponential function and a has to be greater than 0, and a is not equal to 1. So we're assuming that a is not going to be 1 raised to some power, because 1 raised to some power is just 1. That means that if f of x equals a to the x power, we know that its range, from a very standpoint of a basic function like this, is going to go from 0, not including 0, to infinity. It's going to be a positive number. I cannot raise a positive power to an exponent and get a negative result, or even get a 0 result. Now, when a is more than 1 and when a is between 0 and 1, it's going to create other issues. We're going to explore those momentarily. But let's talk about the exponential function f of x equals 3 to the x power. 3 to the x power would itself be a parent function. And of course, all parent functions, we tend to center around x being 0 when we try to discover what goes on there. This requires us to know some exponential rules from previous algebra courses and whatnot. Like, for instance, 3 to the 0 power, or anything to the 0 power, is 1. 3 to the first power is 3. 3 squared would be 9. 3 cubed would be 27. If I have 3 to the -1 power, remember, negative powers means reciprocal. So that's going to be a 1/3. Whereas if I do 3 to the -2 power, I can think of that as 3 to the -1 power squared. And that means I'm doing 1/3 squared, which would be 1/9. And very similarly, if I raise 3 to the -3rd power, I get 1/27. So if I plot these points like this, notice this has a horizontal asymptote on the left only. Because, as we mentioned before, since this is a positive base, I raise it to an exponent, it's going to be positive. But I'm going to get, as I keep making this number more and more negative, this is going to get closer and closer to 0. Since we are, in general, moving up, we can move from left to right, this is considered to be an exponential growth function. Now, there's going to be others as we study them. But that's what an exponential growth function looks like. For example 2, deals with a very similar function, you're going to see a lot of the same numbers in it because we're doing 1/3 to the x power. Well, 1/3 is just the reciprocal of 3. So you're going to see some of these numbers just in different spots. Like for instance, if I do 1/3 to the 0 power, I'll use a different color for this one, that's 1. If I do 1/3 to the first, well, that's 1/3. 1/3 squared, that's 1/3 times 1/3, that's 1/9. 1/3 cubed is 1/3 times 1/3 times 1/3, that's 1/27. These are what we saw for the negative x's on the previous graph. And that's because, and likewise, if I do 1/3 to the -1 power, that means the reciprocal of 1/3, which is 3. If I do 1/3 to the -2, well, that's like having 1/3 to the -1 squared, and 1/3 to the -1 was 3 squared. 3 squared is 9. And very similar, this would be 27. So the exact same numbers, just in different spots here. And again, now this one has a horizontal asymptote on the right, because again, as I keep getting a bigger and bigger value for the x, what I raised 1/3 to, this is going to get smaller and smaller. But this is what we would call an exponential decay. Notice that 3 is a value that's more than 1, and 1/3 is a value between 0 and 1. So given an exponential function, f of x equals a to the x power. If a is greater than 1, then the function is an exponential growth function. If a is between 0 and 1, then it's an exponential decay function. Eventually, we're going to have situations where we need to set up some problems, and if we're being described as having a decay problem, and you end up setting up a function that's a growth function, it's not going to work, and we're not going to find any answers to this. Each graph has a horizontal asymptote at y equals 0 since a of x is greater than 0. Just remember, though, the horizontal asymptote for a growth function is left only, the left side of the graph only, and for a decay function, it's the right side of the graph only. If I wanted to figure out what's going on with g of x here, I'm going to note that the parent function is y equals 3 to the x power, and then I have this table. And so knowing your powers or being able to come up with a list of powers of certain numbers becomes handy, because again, this was 1, 3, 9, 27. These were just the reciprocals. Now I have to look and see. Now I have to remember that my parentheses are technically around the x. I don't really need to have it for that version of it, but it's around it. So anything in the exponent, any operation going on in the exponent is, going to be a horizontal transformation. Anything being multiplied or added to the base is going to be vertical. So when I look at this first one and I say, okay, use graph transformation techniques to draw the graph of this. This is all inside the parenthesis, the 1/2 is on the outside. So when I start defining what my x and y transformations have to be, well, the y, I see multiplied by 1/2 is outside the parentheses. The 3, remember, is the base. It's part of the function. I'm not going to do anything with the 3 because the 3 was already handled by making my table. So my y's are all going to be multiplied by 1/2 because I do exactly what I'm told to do for vertical transformations. So all of these y's are going to get multiplied by 1/2. So 27 divided by 2 is 13.5. 9 divided by 2 is 4.5. 3 divided by 2 is 1.5. 0.5. 1/6, 1/18, 1/54. Now the x's are a little bit more complicated because one, I have to remember that I always perform the exact opposite operation. I have to note the difference between sign of the numbers and the operation. And I also have to make sure that if there's more than one transformation going on, I have to apply the order of operations in reverse. When I see negative x minus 2, I see a multiplication of negative 1 and subtraction of 2. Which means that based on what we talked about before with these, that means I need to first, I see a subtraction of 2, means I'm going to add 2, and then divide negative 1. Each one of these x values I'm going to add 2 and then divide by negative 1. So negative 3 plus 2 is negative 1, divided by negative 1 is a positive 1. Negative 2 plus 2 is 0, divided by negative 1 is 0. Negative 1 plus 2 is 1, we have negative 1. And all these are going to just kind of go, you kind of get the idea of what they're going to be along the way. So now I have what I can do to plot this now. I had a positive a value, but this is a decay. But the reason why it's a decay is because the x coordinate was multiplied by a negative 1 at some point up there, which causes me to divide negative 1. When that kind of thing happens, and I have that reflection across the y-axis, it may look like it's set up as a growth, but as soon as I see that I have a negative exponent or a negative x on that thing, it's like me having the 1/3 raised to a power instead of a 3 raised to a power. So it's going to behave like a decay. So keep in mind that when we obey those rules, it says, a to the x, we're assuming that x does not have a negative exponent on it at that time. If it does, then those rules kind of get reversed about whether it's a growth or decay. Let's look at b. I'm still starting with the same function. Now I'm going to look at the transformations I have, again recognizing that the exponent is where the quantity, where the parenthesis technically is. The 3 is part of the function itself. I'm not going to be doing anything with 3 here because I'm not seeing any kind of operation with 3. 3 is the base of the exponential. And so what I see here on my x's, I see an addition of 1, so I'm going to subtract 1 from all my x's. Remember, I always do the opposite for these horizontal transformations. So when I start setting up my table, all of these just simply go down by 1. The y's, I see a multiplication of negative 1, I see a subtraction of 4. I do both those operations, I follow the order of operations. So I'm going to multiply negative 1 and then subtract 4. So 27, I'm going with the numbers that are easier to compute, the integers. 27 times negative 1 is negative 27. Subtract 4 is a negative 31. 9 times negative 1 is negative 9. Subtract 4 is a negative 13. 3 times negative 1 is a negative 3. Subtract 4 is a negative 7. 1 times negative 1 is negative 1. Subtract 4 is a negative 5. Negative 1 times a third is a negative third, which gives, when I subtract, I'm going to get negative 4.3 repeating. Negative 1 times 1/9 is negative 1/9. Subtract 4, I'm going to get negative 4.1 repeating. And negative 1 times 1/27 is a negative 1/27. And that's going to give me like a negative 4.037 repeating. I mean, it's also important to notice. I mean, remember we have asymptotes on these things, and so I mean I can note here that this had a horizontal asymptote left only of y equals 0. Well, The fact of the matter is, since I have these transformations, if I take this, multiply by -1, and then subtract 4, this would have a y equals 4 as the horizontal asymptote. And I still would expect, and since there was really no kind of like reflection, that affected horizontals, I expect to have the horizontal asymptote still be on the left only for this one. So let me re-emphasize the axes a little bit better on this. And I'm going to plot these points. Since we're getting negatives with this wouldn't really define a situation of exponential growth or decay. It's just, it's a lot of transformations on this. But that's generally how you go through and do these particular transformations. The next thing we talk about with dealing with exponentials is the compound interest. So let's talk about what the formula looks like, and then from that formula, what kind of things go on with it. So compound interest, as far as exponential things go, we have this formula to follow as far as, figuring out compound interest. So we have A, which is the amount after time t. Sometimes you'll see this referred to as the accumulated amount. P is the initial amount, which will sometimes be known as the principal. That means what you're putting in there and depositing originally. R is the interest rate in decimal form. So if I say we have 5% interest, R is 0.05. If I have 7.9% interest, a big issue that students will do is they'll say, oh, 7.9 interest, already a decimal, so 7.9 is R. Well, no, this is still written as a percentage. I need to write it as a pure decimal. That means that R is 0.079. If I say R is 7.9, that's like saying 790% interest. It doesn't make any sense for that, and that's often because they put the wrong decimal in for a percentage. With compound interest, T is typically the time in years, and N is the number of times the interest is compounded in 1 year. Sometimes it's also known as the compounding period. We're going to explore how we handle these in example 4 below, so let's have a look. And excuse the size I have this set at for example 4. It's just that the setup is very similar for all of these, except, anything that's going to be different. I mean, we're assuming that we have an initial investment or principal of $5,000. We have a 6.9% annual percentage rate, so that's our interest rate. Will be worth 10 years, so our T is 10, and they mentioned different compounding periods. So essentially, for all of these, I'm going to have A equaling 5,000 times the quantity one plus R, which is going to be 0.069. I'm going to hold off on N for a second, but the T is going to be 10. So all these are going to be identical in this fashion. All it's going to be different is the compounding period. So when you see compounded annually, that means that I'm just doing this once per year. So N is going to be 1. Semi-annually means N is going to be 2, twice a year. So 2 would be here, 2 would be there. When I see quarterly and N equals 4, I'm going to take the interest rate, divide it by 4, and apply it 4 times in that 1 year. But I'm going to do that 10 times because there's 10 years. Monthly, it's going to be N is 12. Compounded daily, If you want to be overcritical and say 365.25 because of leap year stuff, but we'll just say 365. And compounded hourly, well, you have to figure out, 24 hours a day for 365 days. That's 8,760. You're not going to see many problems asking you to compound hourly. We want to talk about, we want to show though the effect of compounding alone, because in all these instances we have the same starting amount, we're going to invest it for the same amount of time, we have the same interest rate. How does compounding the interest make a difference? So let's run these calculations at this time that I came up with when I calculated these out, following my order of operations and everything. So if I invest $5,000 at 6.9% annual percentage rate, and if I'm only compounding interest once a year, I'm going to end up with $9,744.22 after 10 years, assuming I'm not putting any more money in there. Which, it's a pretty good jump. I mean, I'm going up by 47 $4,744.22. When I compound it semi-annually, so instead of taking the interest and just putting 6.9% at one time during that year, if I take that 6.9%, split it into 3.45%, and apply it twice during the year, that means I'm going to take 3.45% added to the of 5,000, added to the 5,000, get a new amount, and then take 3.45% of that amount, and then add that to the total. I end up with $9,853.26. So you can see, I'm talking about a difference of about a little over $109 there. So I mean, that's a pretty significant difference. If I go quarterly, I ended up with $9,910.10. Now it's even higher, but if you look at the difference, this splits it into four pieces and applies it four times a year. It's not as big of a jump as when I went from 1 to 2. I mean, here I'm going from 9853 to 99110. So I'm going up maybe about roughly maybe $57. A little less than that actually. So I mean, the first one was like a good 100 and some dollars there, 109. This was more like, it's about 57. When I go to the next one, from four times a year to 12 times a year, it's still higher, but the difference between the two is only about 38 bucks. And then when I go from 12 times a year to 365 times a year, well, that's, I mean, it's still higher yet, but the difference from, doing it monthly is only about, roughly about $19. And when I go to hourly and basically, every hour, I've split the percentage into 8,760 equal parts and apply it 8,760 times during the year, I end up with still yet a higher amount, but now, we're less than $1 difference. I mean, so compounding alone will increase the amount of money you get, but there's a limit to it. It only goes so high. It's only going to take it so far. And we're eventually going to talk about an instance where we compound interest, what is called continuously. That means that we essentially take a year, break it down into an infinite number of infinitely small parts, and we take the interest rate and break it into an infinite number of infinitely small percentage points and apply it an infinite number of times. That would be the maximum I could possibly get just from compounding at that interest rate. And we'll talk more about that when we get into some other concepts with it, but it will eventually come. But, there's obviously a limit to this. And this kind of gets into an idea of a special exponential base that we tend to start looking at when we deal with exponential functions. So let's have a look at that. And before you think about it, this is not a typo. It says the number e. It's just like the number pi. This is going to be an irrational number that we're going to define from this. So I'm taking my compound interest formula here, and we're going to assume that we have p equals 1, r equals 1, and t equals 1. So essentially, what we're looking at here is that our formula is now going to be a equals 1 times 1 plus 1 over n to the 1 times n power. And we want to see, okay, well, if I just change n, what happens with this? And here are the values that I get when I do this. And these are just doing some roundings of this number. But as you see, when I just change the compounding of this number, the end value, I get this, it starts at 2 and it keeps increasing until I get to this. And as I go from next higher power, the next higher value of n, and so forth, this starts having a limit where, I start going to a number that's about 2.7182817, so forth and so on. And so what ends up happening is if you keep going and making n bigger and bigger and bigger, the more decimal places stop changing, and you end up with a number as we approach infinity, as n keeps getting infinitely big, that's about 2.7182818,284, and it keeps going on, but there's no discernible pattern to it. It doesn't show signs of being a rational number. There's no repeating pattern in the decimals. There's no sign of termination. This number is what we define as E. So this is what we're calling. It's an exponential base where essentially, and the whole premise behind E is that, growth, it's continuous growth. And that's the idea behind the E. It's assuming that we have continuous growth. Continuous growth, is basically like, like if someone, even if someone has what they call, quote, a person as a growth spurt, it isn't as though, if they grew like 6 inches in a year, it isn't like, during the course of the year they were 5, 6, and then the next thing, sitting in front of you, they show up 6 inches right in front of you and become 5, 6. No, that doesn't happen. That 6 inches growth occurred continuously throughout the year. Well, this E is kind of behind the idea of doing this continuously. When I do the other growth and do compound interest, I'm splitting it into discernible amounts where I am going to have, a sudden jump of value. And the more times I change that compounding period, the bigger that number is, the more continuous the growth is being applied. And that's the way things in biological systems tend to use. So now as we do this graph here, there's going to be a limit to how precise we can be, especially with a value that's irrational. And having all these decimal places, I'm not going to be able to graph it with too many decimal places of accuracy. So for the sake of our exercise here, I'm going to work under the assumption that E is approximately equal to 2.717, which is good enough. Or the 718, take that back, 718. And even now, I'm not going to be able to graph all that accurately, but just for the sake of computations and whatnot. And so essentially, if I, raise that to the first power, I'm going to have 2.718. I raise that to the 0. Anything to the 0 is just 1. The rest of these, I'm going to have to apply powers. So if I square it, I get 7.3, we'll say 87. If I cube it, I get about 20.079. And so I can plot all these points to the best of my ability. 0, 1, one nice thing is that, raising the 0 power is always going to give you a 1. But if I have an irrational number and I raise it to a power, I'm going to have more irrational. So this is about 2.7 something or other here, which I'll say is about there. At the square, it's going to be at it's going to be at 7.387. So we'll say a little under 7.5. At 3, it's going to be at about exactly. It's pretty much at just slightly above 20. As far as the rest of them go, they're going to get closer and closer to the x-axis. I'm not going to be able to get too precise with that, so I'm just going to kind of just graph it at this point. Still looks like a growth function. It's just a different base, that's all. But if I use a table like this, I can come up with an approximate now if I do some other powers of e. And again, the reason why we do these graph transformation techniques is so that I know I'm not missing the important parts of this. Because again, if I have a graph that looks more like this one, e to the negative x plus 2, and I'm going to note here that this had a horizontal asymptote at y equals 0. Because that's also a vertical feature for this. So if I have a vertical transformation, I expect that to be transformed in a vertical way too. And so when I look at e to the negative x plus 2, from what I see there, I mean, again, the negative is inside the parenthesis. That's being multiplied to the x, so I have negative 1 being multiplied, which means I'm going to divide my x's by negative 1, which is the same thing as multiplying them by negative 1. So it's going to change their signs. And the y's, since the plus 2 is on the outside, it's a vertical transformation, I'm going to add 2. Which also means that the horizontal asymptote is going to be added by 2 as well. So y equals 2 would be the horizontal asymptote, which is an important thing to know because I want to know where it's starting to behave like the asymptote so I can start assuming that's where it is. I certainly don't want the graph to go below there, so if I misplot anything, it may cause an issue. So basically all these are going to be added by 2. So if I start plotting those points, and there's a good graph of what that looks like. And if you graph this on the same kind of axis, it'll look exactly like that. So section 5.3, logarithmic functions and graphs. We used f of x equals y, or y equals 3 to the x power as that function to introduce what exponential functions look like and what they do and why they look the way they do. Well, they also have inverses, and these inverses, if you would go through and do the inverses shown right here, switching my x's and y's, I'm actually taking the x and making that, which was once the exponent, and now making it the result, and y is now in the exponent place. And now when I try to solve this for y, until we actually define a function, we wouldn't be able to solve this for y and get that new function. But if I were to graph this function the way it is, as you can see down here, that it just kind of turns like the exponential function on its side. Now we remember from exponential functions that first of all we're only considering bases that are positive, so I'm not going to have any instances where I go below 0. Well, because of that, this has a domain restriction that I can only put in values that are above 0, because it's impossible for me to raise any positive number to a power and get 0, let alone get any negatives. And so where we had a horizontal asymptote with the exponential function, we have a vertical asymptote at x equals 0 for this logarithmic function. And so in order to solve that equation we have up here, x equals 3 to the y power, in terms of y, we define a function, we call it the log. And it's usually the log base 3 of x. That's the inverse of 3 to the x. So, if f of x is the log is 3 to the y power, 3 to the x power, then the inverse function, and it is a one-to-one function. Notice that the above does pass the vertical line test as well. It's going to be the log base 3 of x. So these are inverses, and basically whatever the base is here is going to be the base here for that function, for the logarithmic function. Now, one of the things they're going to ask you to do along the way is be able to translate an exponential statement into a logarithmic statement, because that's generally what we do when we go through the process of solving an equation, or solving an exponential equation. We turn it into a logarithmic equation, and vice versa. If I want to solve a logarithmic equation, I turn it into an equivalent exponential equation, and then I should be able to, deal with doing the exponent in that case, or vice versa. So these basically say the same thing. This one here, the exponential statement says, essentially, if I were to read this out loud, and I'm going to write what it would say, it says a to the power b is c. Whereas the logarithmic statement, if I want to translate it more into English, I would say the power of a that gives c is b. Or I can even say the exponent a is raised to get c is b. And so those are basically the way you would translate that into English. They're basically saying the same thing. Since exponential functions and logarithmic functions are inverses, keep some things in mind here. As we said before, for a function that's exponential, our a is greater than 0 always. The domain could be any. I can raise this to any exponent I want. Okay, there's no problem with that. The exponent could be anything. The range, on the other hand, well, since I'm taking a number that's positive and raising to a power, it has to be more than 0, and that's basically what this is saying. It's saying basically, I could say that f of x, essentially f of x is greater than 0, and it's really thick again. So now here, on the other hand, kind of we talked before, the range of this function becomes the domain of this function, and the domain of this function becomes the range of this function. So the domain, this number I plug into a logarithmic function, it has to be more than 0. Which means, you're not, if you see a statement that says like the log base whatever of 0, or if I say the log base of some negative number, these are undefined. They don't exist. You can't do them. In some pre-calculus, you could actually learn how to handle this and bring in complex numbers, but we're not getting into that in this course. So, but for our purposes, for our logarithmic purposes, the number has to be positive. We're really looking for real solutions for logarithms here. And so, the first one here, given this information that we've looked at, for the example 1a, you're asked to convert the equation log base 4 of x equals a to an exponential equation, and then you're asked to do basically the opposite, convert the equation 5 to the x power equals b to a logarithmic equation. Part A, remember that I always recommend start with the base. The base in this one is 4. So I'm starting with that base, which means that the base of the logarithm should be the base of the exponential function. As far as the rest goes, it's just basically switching places across the equal sign. The x was on the left, so now it's going to be on the right. The a was on the left, on the right, so now it should be to the left. And for me to apply an exponential base to something, that means that a has to be the exponent. And so this is 4 to the a power equals x. In a very similar case with b, this is the base, so I'm going to be starting with log base 5. I'll put my equal sign down, and then I basically am going to have this transition across the equal sign. So the x is going to be on this side, and I always take the log base 5 of a number. And I also say, for the sake of argument, because sometimes you'll start doing expressions and things like that, get in the habit of thinking of this as having a parenthesis around it. That's certainly the way it's going to be presented on your calculator at some point, because logarithm as well as exponential functions, They imply, I mean, they're their own functions. So when you're asked to do transformations regarding them, you have to kind of know where the parentheses are and handle them appropriately. Now moving on your calculators, if you have a TI calculator, these two are buttons that are actually on your calculator. And these are the logarithm buttons that all scientific calculators will probably have on them. Graphing calculator is going to have them on there. And this is basically a log base 10. So if you just see log and you don't see any exponential bases, you assume it's base 10. We had the e to the x power equals y. So its inverse obviously is going to be the natural log, of y equals x. So, so basically the same thing with this, if I'm converting it to statements. But these are the ones that show up on the calculator. Now, newer versions of TI-84s, there is a log base command. And what that will do on your calculator is you'll actually see it set up with, it actually will put the boxes here, so you could say you could put, the base here and the number here, and it'll do any log base. But as I said, that's on newer versions of TI-84s. So you have to make sure it has a certain operation system on them that will have this command on there, and they don't make it easy to find either. You have to either go through the menus on there and search, or you can actually hit alpha in the window button to find that. I'm not going into the ins and outs of using that calculator. You're welcome to use it to your heart's content. However, a lot of the questions you're going to be asked dealing with logarithms, especially once we get towards the final exam, are going to give you things that you have to use various rules and properties that we'll be talking about as we move further into this. But for the time being, you're asked to do the following. For example 2, you're asked to graph a logarithmic function. In this case, let me zoom out a little bit here. The log base 4 of x, and use that to draw a graph of this function, which obviously, if log base 4 of x is the main function, this would be a transformation of that function. So let's get into this so we could do this, and I'll just zoom out just a little bit more to fit this in. So now remember, what I'm looking for here for the y's should be exponents that I'm raising 4 to get x. So basically y is going to be the exponent. So what I want here, to make log base 4 of x work, I want to have powers of 4. And I want to make sure I have a little bit of everything. So as I come up with those powers of 4, obviously, 1 is a power of 4. It's 4 to the 0 power. So this would be a 0. So other powers of 4 would be 4, 16, 64. The next one would be 256. These represent basically your 1, 2, 3, 4. These are the exponents that would raise 4 to get the numbers that I have for x. And of course, I also want to consider things like, 1/4, which would give me the -1, 1/16, which would give me the -2. And so I'm going to graph this on here. And of course, that y-axis is the vertical asymptote. So that's a log base 4 of x I graphed there. And I'm graphing it lightly because ultimately I wanted to have the transformation. So now the transformation, I'm just using the same old techniques. I do have a horizontal transformation. I have the -5 inside those parentheses. And the parentheses being defined by the logarithm. Okay, so be careful. Sometimes they have a tendency to say, okay, well, if I do 2 log base 4 of x -1. I'll see they'll do something along the lines of that and say f of x equals that, and then I'll have people say, well, the 2 and the -1 are both horizontal transformations because they're inside parentheses. But remember, the main function is this. In actuality, you really don't even need the parentheses in this version of it. That -5 in there tells me I'm going to add 5 to each of those x coordinates I have over here. So 5 and 1/16 is 5.0625. That would be 5.25. That would be 6, 9, 21, 69, and 261. And as far as the y's go, the 2's on the outside of that parenthesis, so all of them get multiplied by 2. I did exactly what it says. So this would be -4, -2, 0, 2, 4, 6, and 8. And so when I plot those points, and so those graph transformation techniques still come in handy for us, to graph an accurate version of the function. I just have to know how the original function works, and then if any additional operations I have to account for as I go through and work on that. In example 3, this is just about mostly putting this into your calculator, because these things, even if you rewrite these as exponentials, right here, if I consider this to be like, okay, equals x equals x equals x, this is basically this is a log base 10, so I'm looking for 10 to what power is 314. Well, you're not going to know that off the top of your head, because 314 is not an integer power of 10. Your integer powers of 10 would be 10, 100, 1000. So I can tell you that x is between 2 and 3, but I want to get a better value of that, so that's time to put it into your calculator. Same thing with this. This is basically saying e to what power is 6. Well, e is an irrational number to begin with. What can I do to get that to be 6? Well, you're not going to come up with a number like that, so it's time to put it in your calculator and just type this in. Here I'm basically saying -5, or take that back. 10 to what power equals -5. Well, that should give you a self explanation at this point, as far as what that answer is. So if you do these on your calculator, if you do log of 314 on your calculator, rounding to 4 decimal places, you get about 2.4969. And I do often recommend rounding to 4 decimal places, trying to come up with an approximate answer for the sake of going back and checking it. If you just keep 1 or 2 decimal places, and you try to check it, putting it into your calculator and going back to the original equation eventually or anything like that, the natural log of 6 is approximately equal to 1.7918. Again, that's just mostly put in your calculator. For C, it's good to keep an idea about this and always think about it, but also think, you could probably say, well, just knowing what the domain of a logarithm function is, or when it's translated to an exponential function, it should be clear to see that there's no way I could take 10 and raise it to a power that gives me a -5. So this is no solution, or undefined, whichever way you want to say it. It means the same thing. Well, technically it should say no real solution. You can do logarithms of negatives. There are ways of dealing with that. That gets into complex number theory, which is something that is done quite a bit in the pre-calculus course, Math 200. So now for example 4, it's a very similar question, except the fact that these are instances where you're being asked essentially to do things where you should be able to figure this out. Like for instance, log base 3 to 27. I can rewrite this as an equation and say, okay, if I rewrote this as an exponential equation, 3 to the x power equals 27. So I'm looking for what power of 3 is 27. Now 27 happens to be a perfect power of 3. As a matter of fact, 3 to the x power equals, it's 3 to the third power. So if I have an equation that looks like this, well, 3 to the x power equals 3 to the third power, that means that x would have to equal 3. Well, for this one, again, if I want to rewrite this, I can say that 2 to the x power is 1/8. Now you might be saying, okay, well, wait, is 1/8 a power of 2? Well, it is. First of all, I could do a couple of things to this. I could say, okay, well, that's 8 to the -1 power, going back to some exponential rules, to the x power. Now, 8 is 2 to the 3rd power, 2 times 2 times 2, which means this is 2 to the -3 power. So again, as I have 2 to the x equaling 2 to the -3, it means x has to be a -3. Now this one here, I'm not going to go as far as making this an x. I could keep doing it this way, but if I have a log base 10 of a power of 10, well, if I rewrite, okay, well, what power of 10 is this? This is 1 over 100, which is the same thing as 10 to the -2 power. Anytime you have a logarithm right next to exponential of the same base, as long as there's nothing between them, so there's nothing in here like a multiplication going on or anything like that, then they just cancel, -2. So if I look at the log for D, log base 10 of 10 cubed, these cancel. This is just 3. This is the log base E of E to the 5. And much like I had in C and D, I have a log of the same base right next to an exponential of that same base. Nothing in between them, no multiplications going on onto E or anything like that. That had to be handled something differently. So if that happens, they just cancel, and you're left with just the exponent. Takes a little bit of ingenuity here. Again, this is log base E. 1 over E squared is the same thing as me 7 E to the -2 power. And that's going back to my exponential rules again. So again, with nothing in between the log base E and the exponential base E, since they are the same bases, just inverse functions, I just left with the exponent -2. So those are pretty easy and straightforward. I mean, as soon as you can either do them this way with the equation and kind of figure it out, or use the new shortcut that if I have a log and an exponential that are the same base right next to each other, no other things going on between them, then I can just cancel out those and be left with that. Now, when you get to these questions down here, obviously it's a little bit of a problem. 17 is not, let's zoom in a little bit here, 17 is not a perfect power of 4. 3/4 is not an integer power of 5. There's nothing I can raise 5 to that comes to be 0.75. What do I do with these cases? Now, as I mentioned before, if you have that log base formula or command on your calculator, you could use that, and they'll come up with these answers beautifully. The problem is, again, even if you have it on your calculator, finding it could be problematic. As I said, I'm not going to spend time demonstrating how to find it on here, because my goal is not to teach you how to find it on the calculator, just have it do it for you. It's a nice feature, but it's a feature you won't have when you take the final anyway, so you might as well not get used to using it. To answer questions like this, we use what's known as the change of base formula. The change of base formula, very useful, before that command was put into the calculator. Still useful now if you don't feel like searching for it. Basically, it says I could take a logarithm of base B, and we're assuming that base B is going to be a base that isn't on your calculator immediately. If I do the log base 10 of M over the log base 10 of B, I'll get the same answer. I could also work with natural logs. And so whenever I go to do the problems now, so if I go to do like the problem for log base 4 of 17, technically I could rewrite that as the natural log of 17 over the natural log of 4. Either one of these should work. And if you put this into your calculator to come up with an approximate value, this is 2.0437. This is going to be the log base 10 of 3/4, or natural log. I'm just going to do one of them this time, just do log base 10 over the log base 10, which means I don't write it, of 5. And so if I do that, -0.1787. Anytime that you have a number in here that's below 1, expect to see a negative when you do that, whatever the logarithm is. But that is the end of this lesson and this video. If you have any further questions, please make sure to bring them up in class, or come and see me during my office hours. Until I see you in one of those places or until the next video, have a good day and I'll see you around.